Okay, so we're going to work with chapter 9 today. Someone remind me at the end that I want to discuss our approach to the final. Okay. All right, so first things first is simplifying radical expressions. Radical expression contains a radical, which is why it is called a radical expression. So here's the important parts of the radical. We have what's called the index. So typically what you guys are used to working with is the square root function. Okay, you're used to the square root. And because there's no understood one, if it's a 1, it's just a regular expression. There's nothing else extra. So for a root 2, that is what we consider understood. So if you just see the square, that's it. It's a square root. If you see an actual little number written here, then it's what's called an index. So then you can have cubed root, fourth root, squared and cubed are pretty much your special names. The rest of them just go by the number and then th. So that is your index. The radicand is what's underneath the radical sign. I would say 98% of the population just calls this a square root symbol. So it's fine if you want to call it a square root symbol. I know what you're talking about. And then all of it together is what we call a radical, right? I'm probably just going to work within the board today instead of the whiteboard. I'm probably just going to work within the PowerPoint because I want to show you too many of the slides and I don't like going back and forth between the two. So, okay. So here's the first question you have to ask yourself. When you're dealing with this kind of thing, you kind of want to look at it as almost a reverse multiplication problem, kind of. You want to ask yourself, how many times itself would one number give you -8 3 times? Does that make sense? So like there's a number out there that if you multiply it by itself 3 times, you're going to end up with -8. Does anyone have an idea of what that number might be? So another way to look at these problems is you want to think of what number cubed will give you the number under the radical sign.
Is it -2?
It is -2. And you can prove that by yourself. Whoa, what just happened there? Why did that? Okay, weird. All right. Okay, so we can prove it to ourselves by saying, well, let's try -2. -2 cubed. -2 times -2 times -2. Well, negative times a negative is a positive. Positive times a negative is a negative. 2, 4, 8. So -8. So it checks. So your answer here is -2. Okay. All right, so same approach for the fourth root of 81, except you're not asking yourself how many times a number times itself 3 times, but a number times itself 4 times now. So I will let you know that you can put these into your calculator. You can get answers out, so don't go like banging your head against a wall. I'm just trying to help you also, if you wanted to know how to do it without the calculator, these are the questions you ask yourself. So what do you think the fourth root of 81 is?
3.
Yes. Okay. So if you wanted to justify it. 3 to the 4th power. Well, that's 3 times 3 times 3 times 3. So 9 times 9, 81. Okay, so 3 is your answer. Now, does anyone need me to explain how to put them in the calculator? Yeah? Okay, so 2 different ways depending upon how your calculator works. If you have a lower calculator, the way you want to do it is you want to take the radicand. So for this one, it would be 81. And you want to put it in a parenthesis set. And then you'll use the caret. And then here's where it gets a little tricky. You want to have it to do the 4th root and not the power of 4. So you're going to do 1 over 4. And that should give you the number 3 out. The other way you can do it is if you hit the math button on your calculator, you should see a cubed root, and then underneath it should be an x root. So you put the 4 on the outside. So it would look like this, 4x root 81. And that would give you 3 as well. Okay. If you need help with that kind of stuff, let me know. I can always help you. Anybody think we need to save this? I'll save it just in case. Why not? Any questions on this type of problem? Okay. You by all means can solve them with your calculator or with a calculator online. So, oh, and look, they were nice enough to also show you how to put it in your calculator. Pretty cool. Okay, cool. All right. So
is this from the PowerPoint, right?
Yeah.
Okay.
And I don't believe it has them individualized, so it's just the big PowerPoint.
Okay, well, I just printed it out. That's what I was doing. So
Yep.
Okay.
All good. So then writing exponential and radical forms, basically the way this example series works is if they give it to you as a exponential, they want you to write it as a radical, and then vice versa. So let's work on that. Okay. So number 1, is that written in exponential form or is that written in radical form?
Exponential.
Very good. So here's how we basically go from one to the other. Now, before I told you if you were taking the 4th root, you would raise it to the 1/4 power. So we're going to do kind of the same thing. We know it wants to have a radical. We know the radicand is x because that's the base. And then we just have to figure out our 3/7. So what do you guys think? If our last example was the 4th root of 81, and I said another way to write it in the calculator was 81 raised to the 1/4. If you guys kind of look at that example, how do you think we're going to finish this problem out? Look at where the 4 is in the radical and look at where the 4 is in the fractional exponent. Try to use that to help you with this.
Are we basically going to put the 7 on the outside?
Yeah, we're going to put the 7 in for the index, and the 3 is actually going to come underneath as a cube for the x. Does everybody see that? Okay. All right. Now, number 2 is in radical form, so they want us to basically reverse it and put it into exponential form. So our base is going to be our radicand. It's just x. But then what's my exponential going to be? What's my exponent?
5/2.
5/2. Good. Now, where did Mara get the half from? How did she know it was going to be 5 halves and not 5 anything else?
Because it's just a square root. There's no
Very-
other number there.
Very good. So we have what's called the understood 2 there. If you really need to write them in, you can, but at this point, you all should really understand that that's a square root. But obviously, when you're manipulating things, sometimes you can go too fast and forget. So if you need to write that out, go ahead and write it out. All right, so number 3 is in exponential form. And again, we're just going to reverse it. So what do you guys think we should do? So we know we're going to have a radical. What's going to go underneath the radical?
The 3w plus 1.
Mm-hmm. Right? And then now we just have to worry about how we're going to split up our exponents. So what do you think we're going to do?
Would 5 be the index?
Mm-hmm. Mm-hmm. 5 is the index, which means the 4 is just going to come underneath as an exponent. Okay. And I'll help you guys out with the last one. We're going to have 2x plus 5. And we're going to raise it to 3/8. What do you think are some mistakes students could make on these so that you guys hopefully don't make them?
Switching the, like, where they go.
Mm-hmm. So another thing I would never want you guys to do is if you do bring them in, so let's say you do switch it up. Let's say you do mix up where it's supposed to go. As long as you put one of them in the index and one of them in the exponent, I'm not going to take off as many points. What you don't want to do is make them big numbers. So you don't want them to come completely outside the radical, and you don't want them to become a big number inside the radical, okay? They're little numbers for a reason. So try to keep that in mind. They're either going to be an exponent or an index. They're never going to become a big number, okay? All right, let's keep it moving. All right. You guys can see their solutions if you want. All right. So this is one of the slides that I wanted you guys to be able to take a look at. It is the perfect nth power. And this is why this will help you. As we simplify radicals, as we work with the operations of radicals, people really want to see radicals written in simplest form, much like with almost everything else we work with in algebra. So if you memorize some of these, if you kind of figure out, what is a perfect square, what is a perfect cube, how do you get to a perfect fourth root or fourth power, you could potentially have to keep going too. So as long as you kind of get these simpler definitions down and kind of memorize those, that'll help you going forward, okay? And definitely if you're someone who takes written notes and doesn't go back later, or even if you do go back later, definitely want to write these down just once. It's not something you have to memorize, but definitely something you should be aware of. So the product property of radicals. Multiplying radicals, for the most part, are pretty easy. When we start to get a little bit confused will be when we do foiling. There's actually two different ways to foil. They kind of give you what they consider a shortcut. You can obviously use either approach. Sometimes it's actually nicer to use their shortcut, but most of the time I'm a little bit defiant and I just do the foiling. But you guys can make your own decisions. Here are some guidelines. If the radicand has more than one numerical factor that is a perfect nth power, select the largest one. If the radicand has more than one factor that is the perfect nth power with the same variable base, select the one with the largest exponent. Obviously, those guidelines are not really going to make too much sense right now. In fact, I don't even really know if I cover those like typically. Okay, so let's actually get in and do some practice because I feel like that teaches you guys the most. All right. So the PowerPoint breaks these down a lot easier than I do. I kind of take less steps. So if you need more steps, you can by all means check out the slide answers, but I don't take as many steps as they do. So what perfect square is within 48?
Would it be 12?
So 12 is not a perfect square, but it does include a perfect square. So if you wanted to take that approach, you could use it. 48 actually divides nicely by 16. So 16 times, and then I like to do things I know I'm going to take out. So 16 x to the 4th, y to the 12th, and then I know that I'm going to have 3y left. That's how I like breaking it up. If you guys want to leave it separated out more, that's fine, but this is the approach I use. So if we kind of look at it as this own individual problems, what's the square root of 16?
4.
Mm-hmm. And then we have x to the 4th. So what's the square root of 4?
2.
Mm-hmm. Now, y to the 12th is a little bit different. Because they're exponents, you kind of have to think of it as pairings. So how many pairs are in y to the 12th?
6.
6. And then 3 does not have a perfect square in it, and y does not have a pair with it. So that is your overall answer for this problem. When I taught high school, the way I taught square roots and radicals and stuff like that was basically like, we all know what toll roads are, right? We all hate them. We try to avoid them immensely. But when you get to a toll road because you have no other choice, you have to pay the toll, right? Radicals are the same way. In order to go out from the radical, you have to pay. So you have a pair when you're inside the radical, but then you have to pay to get out. Does that make sense? So that's why you only have one of the pairs on the outside. All right. How do you think we can rewrite the next problem so that we can easily bring something out? How do you think we can rewrite it? with the square root, do we like even numbers or odd numbers? If we want to find the pairs.
Even.
Even. Okay, so we're going to split this up into 5x plus 3 to the 8th power, and then just 5x plus 3. Now I can do that because they're being multiplied, and 8 plus 1 gives you 9. Okay, how many pairs are in 8?
4.
4. Very good. So we're going to bring out 5x plus 3 to the 4th power, square root of just 5x plus 3. And that is that answer. Any questions?
I do have a question.
Yeah.
So, oh, it's the square root. So, but I thought this, isn't the square root of 9 3? No.
Yes, the square root of 9 is 3, but you have to be careful when they're exponents. You're looking for pairings. So I guess I said it a little bit wrong when I asked you what the square root of 4 was. It just so happens that there's 2 pairs in it, and it's also a perfect square. So x to the 4th power is not a good example. The reason why we can't just
Now
say,
I'm confused.
now you're super confused. Okay.
Yeah.
So
So why couldn't it just be 5x plus 3 to the 3rd power?
because if we did that, if we did 5x plus 3 to the 3rd power, and we wanted to then square it, you would get 5x plus 3
Oh, okay. No, I get it now. All right.
to the 6th power.
All right.
That's
Yep.
why it doesn't work.
Okay. Now I got it.
All right. Excellent question. You're going to do great in trig next year, because that thinking, you know how you wanted to experiment with that? I know this is a sidetrack, but any of you that are decide that you might want to take 165 or 160, that thought process of why can't I do it this way, or why isn't it this way? That's how I teach my trig class. When my trig students say, well, why can't I take this approach, or why won't this work? It's my first semester teaching it. I by no means know it nearly as well as I know algebra. So I literally tell them to try it. And most of the time they end up going, yeah, you're right, it didn't work. But I don't care if you guys want to try things, just make sure you talk to me about it, because chances are it's not going to work. And I don't want you to be confused. And the algebra, I definitely know like the back of my hand. All right. If you guys want more of a breakdown, it's on the next 2 slides. All right. Okay, so here's a few more examples of simplifying radical expressions. You need to make sure that you always simplify into lowest terms if you can. So this one's kind of unique. So what we have to do here is we have to rewrite it in order to kind of simplify it, and then we rewrite it as a radical again. So we're going to change this to an exponential. And remember my index goes on the bottom, so then it's going to be 8 over 12. Is 8 over 12 in simplest form? No. So what's 8 over 12 become?
Thirds.
2/3. Very good. So 3x plus 7 raised to 2/3. Now, it just kind of depends on how Pearson's problem is set up. They could have you stop there if they don't care about the form. If they care about the form, they tell you it wants to be in lowest radical form, then you have to make sure that you put it back into a radical. If they don't care, they just want it in lowest form, then you can leave it in exponential form. As far as I'm concerned, as long as you simplify it, you can either leave it as the exponential or you can leave it, you can go back into the radical. Doesn't matter to me. So number 2 is going to follow the same process. If you're following along with the printouts and not the PowerPoint, I think it's letter D, 7D. So if we're going to rewrite this, it's going to be 1. Nope. Oh, I see what they did. They kind of cheated. I don't know how much I like this problem. So before they rewrote it, they put 4 into exponential form. So then they have a base of 2 to the 2/10, which makes it 2 to 1/5. So then they did 5, the 5th root of 2. I guess if you wanted to, if you wanted to verify that in the calculator, you can. You can take 4 raised to the 1/10 power, and then you can take 2 raised to the 1/5 power and verify that. They're definitely going to equal, because you can write 4 as 2 squared. They're going to equal. But if you really wanted to prove it to yourself, you could put it in the calculator like that. But that is the final answer. Okay. Number 3. Can anyone else do it? I'll give you a step for it. What do you guys think? So remember I told you guys that you have to pay the toll. So you want to only bring things out that have the 4 with it. So what can we bring out?
3 to the 4th.
So we're not going to bring out a 3 to the 4th, but we are going to bring out a 3 because the 4th, it's like you're paying that. So we can bring a 3 out. What else can we bring out?
X.
We can bring an X out. And then we have to leave X squared in there because it doesn't have enough to pay the toll. That is an exponent. Don't be confused. Great. So the last one is slightly more complicated. We have to write the exponent form twice. So what's underneath the radical is the square root of t. So t to the 1/2. And then the cubed root is actually written as 1/3. So then we're going to take t to the 1/2, and then we're going to multiply it by the power of 1/3. So you're going to end up with t to the 1/6, which is the 6th root of t. These problems, basically, for the most part, you just have to do them. There's not really any nice way about them. Do you guys have any questions? I saved it and it'll be on the video. So there's it slightly nicer than the way I wrote it. So for number 3, if you really wanted to, you can verify it with the calculator. I mean, you can do that if you want, your choice. Okay, so simplifying a radical expression, you want to find the perfect nth power factors of the radicand. So that was whenever I pulled stuff to the front that I knew we would be able to take out. Apply the product property for radicals, find the nth root of each perfect nth power, and write the radical as small as an index as possible. So that would be why they make you just rewrite it. It might seem a little bit redundant, but that's just the way convention is. All right, let n be a counting number greater than 1. If n is even, then if your index and your exponent on the inside match, then it's equal to the absolute value of x. If n is odd and the index and the exponent match, then it's just equal to x. That's definitely probably something you want to write down. No, it definitely is something you should write down. Okay. So we can kind of use that approach with the next problem a little bit. I'll show you when we can do that. Okay, so f of 14, we're just going to plug 14 in for the x value. So you have the cubed root of 2 times 14 minus 1. Well, what does 2 times 14 minus 1 give us?
$27.
Right. Gives us 27 on the inside. What's another way to write 27? What's another way to represent the number 27?
3 cubed.
Excellent. What do you notice about the index and the exponent? They match, right? Okay, so because they match and they're odd, the answer is just going to be 3. And you already know that anyway, because you pay the toll and you only get a 3 out. So, but I wanted to use that little thing for you, so I did. All right, so we're going to do the same thing for 6. We're going to plug it into the x for the f function. So 2 times 6 minus 1. 2 times 6 is going to give me 12 minus 1 is 11. Can I do anything with 11? No, it's prime. I'm done. There you have it. All right. G function. We're going to plug it in. So negative 3 times the square root of 16 plus 7. Okay. If we really wanted to use that other approach, we could rewrite it as 3 square root of 4 squared plus 7. 2 and 2 match. The absolute value of 4 is 4, so 3 times 4 plus 7. So negative 12 plus 7 will give us a negative 5. Boom. Any questions on that one? Like I said, a lot of it you're just going to have to practice. And this stuff should be kind of slightly review for you. You know how to plug into a function and get the answer, right? All right. Are we good to go? All right, cool. I know I record for you guys, but I do still like to make sure that you're okay in session too. So there it is, written a little bit neater. They actually chose not to practice what they just showed you. So at least we have that. All right, so now we're starting to get to why we're staying in the PowerPoint for this chapter. I am not going to sit here and try to graph with you, not on the, like if I was standing in front of you on the whiteboard or the, you know, the, yeah, the whiteboard, isn't that what we call the thing we write on with markers? Yeah, that thing. It's one thing if I were to stand there and try to sketch this out for you. I'm not going to butcher it on the regular whiteboard for this thing, okay? I don't make my trig students watch me try to be an artist. I am not one, by the way. Art is very nice and it's extremely mathematical. It's just not the math I can do. All right. So if you were given the square root of x as your function, then you want to basically, you're just going to put all your x's that you've picked into the square root of x, and you're going to get your y's out. Okay, so the square root of 0, square root of 1, square root of 4, square root of 9, square root of 16. Okay, now they obviously picked perfect squares for a reason. They're not going to sit here and give you decimals, because that would be pretty gross to sit here and try to graph, right? So you want to pick smart options. All right. Now it says use a graphing calculator to draw the graphs of the following radical functions. You don't have to do this. You can if you really want to. I don't think most of yours will come out multicolored. So, and I don't really feel like the one they used should have been able to be multicolored. I don't know how they did that. That was some math magic right there. They definitely did not use, they are showing an older calculator, but they definitely used a newer one to do that. All right. I believe I told my trig students too, I would not use your regular calculator to graph some of this stuff. You can if you want, but I think what ultimately ends up happening is sometimes your calculators kind of don't like it. They can do it and they're smart enough to, but then when you want them to do something normal, quote unquote, you have to reset it. So I honestly recommend that you just use Desmos for graphing any kind of radical equations. I would not use your regular calculator. Desmos is free. I don't do a lockdown browser, so you can use it on the exam. I would recommend using Desmos. All right. A radical model is a radical function or its graph that describes an authentic situation. Examples include rise in temperature of an enclosed car, hopefully not with any pets or children in it, the period of a planet, the length of a braking car's skid marks, and the percentage of an email that is spam. I don't even want to know what that percentage is. It's disgustingly high. And then a square root model is a square root function of it or its graph that describes an authentic situation. So basically, if you're seeing the word model, you should know that a word problem is coming up. That's basically what they're trying to tell you. All right, so we're going to use the following information to make a prediction. So the percentage of foundations that compensate all of their board members are shown in the table for various assets. So asset group, millions of dollars, asset used to represent asset group. That's weird. And then percent. And they apparently got this from the New York Times. So what they basically did here was obviously formatted incorrectly, but they pretty much, they found the class range mid. So they took the class range and they found the midpoint. Obviously, you guys know from when you did your scatter plots that you can't put in 0 to 5. You have to have some kind of class representation. So all they do is they find the midpoints, and that's what they use. So when they put this in to do their scatter plot, they use the middle column and the last column, okay? All right. So they say let F of A be the percentage of foundations with assets of $8 million that compensate all of their board members A model of the situation is given as f of a equals 1.5 square root of a plus 4. You're going to use a graphing calculator to draw the function, and then in the same window, they want you to do the scattergram. Estimate the percentage of the foundation with assets of 30 million that compensate their board members. We're just going to go through it. I'm not going to sit here and have us try to do that right now. You, by all means, can do it on your own time. In fact, it's highly encouraged. I believe you can also do it with Desmos, but you have to do it kind of interestingly, so I would definitely watch a YouTube video on it. The graph of f and the scattergram, wow, of the data shows that the model appears to fit well. Obviously, you can see that because look at how many points actually hit the line, okay, or the curve. Now, if we're going to evaluate f at 30, that just means we put 30 in for a. And then when you evaluate that, you get out about 12.2% of foundations with the assets of 30 million compensate the board members. Okay. All right. So that was section 1. Okay. We have like, what, half an hour left, something like that. So let's keep rolling. All right. This next part is probably going to be something that you guys will not like nearly as much. We are going to add or subtract like radicals. We can use the distributive law. And when we add or subtract like radicals, we say we combine like radicals. I don't know why you needed to be told that, but okay. So let's do some of these. All right. First question for you. Square root of x and square root of x. Does that look like it's maybe able to be represented only once? Okay. You kind of have to look at these as if they were variables, but they're very, very picky variables. So I don't know if you guys have like, I don't know, someone in the family or someone that you know that's like absurdly particular about things. That's what it's like to add and subtract radicals, okay? So we have to be extremely picky. The next one is just as nice. It gives us the 5th root of 3xy squared. They're the same in both, right? We don't have anything different, so we can go ahead and just subtract them. What do you notice about number 3? Or I guess it would be 11C if you're following along on the other paper. So we have x underneath. So the radicand is the same. But what do you notice about the indexes?
They are not the same.
Correct. They are not the same. So it's already simplified. Oh, man. Writing and spelling. Do you know how hard this is for me, guys? First off, spelling in general is very hard for me. I hate the English language and I hate words, but I love reading and I kind of like writing, but I like writing when I'm typing. This makes me have to use my mouse, remember to use the part of the brain that makes my fingers work with the mouse, and then also have to spell on top of it. It's very difficult. I'm just throwing it out there. Now, for number 4, we realized that our indexes are the same, but what can you tell me about the radicand?
you have one positive as well as one negative, like
So
that in the problem.
So the negative is in between. That part doesn't necessarily matter. But you have a radicand that's x and a radicand that's x plus 1. Are those the same? No. So because they're not the same, it's already simplified. Typing, much better.
I have a question about that. So could you just look at that like with any problem anytime and just like know it's already simplified from looking at it like that?
If you have different indexes or if you have different radicands, yes. The only other caveat I will tell you is if you look at something, and let's say for number 3, that was 4 cubed root of x cubed, then you would have to simplify it that way first. But these were
Okay.
already simplified to the point where they wanted you to know, could we do anything else with it?
Oh, okay. I gotcha.
Mhm.
Thank you.
Okay. All right, so once again, for those of you watching the video, there's a nicer representation of the answers. And then here is a much longer explanation of why 3 and 4 are already simplified. Okay. All right. So these ones, I think Cody kind of hit more on what you were asking of if we can just look at it. So you can see here that we're going to have to actually do a little bit of work before we can decide if we can bring them together. So we're looking at square roots for actually both cases. So I'm going to go ahead and write them with the perfect squares. So we only have one W. 45 has what perfect square in it?
9.
So 9 times 5. So what I like to do in these situations is I try to find the perfect square of one of them, and then 9 times out of 10, you're going to be able to find a like factor in the second one. So we know that 5 times 4 gives us 20. So we have another 5, and we also know that 4 is a perfect square. So we're going to pull out our perfect squares. So we're going to get 3 square root of 5w plus 2 square root of 5w. Right. And then we can see that we have the same indexes, we have the same radicand, so we're going to go ahead and just add the outside terms. Okay. Now, before we do number 2, what do you guys think is a strong likelihood for a mistake a student could make when adding and subtracting radicals? Do you think it's likely that if they didn't have someone sitting here explaining to them that you leave the radicand alone, that there's a potential they could try to add the inside numbers as well? Okay, you don't want to do that. The radicand should be the same once you simplify, okay? So you can manipulate the radicand while you're trying to pull things out of it, but once it's down to its simplified form, that has to stay the same. They have to match, right? So you don't want to go through and try to add those. The difference, of course, will be when we start multiplying. So don't get confused. All right, so 3a cubed. Do you think we can do anything with 3a cubed? what can we do with 3a cubed? How can we split it up if it's a square root?
You can pull a squared out.
Very good. So we're going to split it up into a squared times 3a. So then that means on the right-hand side, or right, the next radical, we should have a factor of 3a. Okay, so let's try it. So b squared is definitely coming out. Well, 12 divided by 3 gives us 4. So that factor of 3a is definitely there. So let's go through and pull things out. So we're going to pull out an a. With the 3a left inside. That looks very gross. I will rewrite it. Minus, and then we're going to pull a 2b out. 2ab with 3a left inside. Okay, so does everything match up? In the radicand, does everything match up? It does. So we can just go ahead and subtract the outside numbers. So 3ab square root of 3a. So this stuff is really tricky. If we didn't have an AB and an AB on the outside, could we have subtracted? No. So you have to think about, not only do you need to have a like radicand, but you're also going to need to have like terms. Okay, it's very, very tricky stuff. It's quite honestly, it's like, no offense if anyone is, but it's almost like inviting the world's pickiest eater to the holiday, okay? So that's what radicands and like terms are with them, okay? They're very, very picky, all right? There's a little bit nicer of a writing of it. They used obviously way more steps than we did, but we still got to the same answer. All right, so we're switching gears a little bit, and we're going to now think about products and multiplication. So these are a little bit different. How do you think they're a little bit different? Don't just say, well, now we're going to multiply instead of add. I don't think I can truly drop kick you through my laptop because obviously I don't want to break it, but the feelings would be there. All right, so yes, we are going to multiply instead of add or subtract, but we're now going to actually manipulate the radicands as well, okay? So we're going to multiply the outside numbers with the outside number, and then we're going to multiply the radicands together as well. So 2 times 5 will give us 10. And then we'll have square root. 6 times 2 will give us 12 x squared. Now, am I done? No, because 12x squared can actually be simplified when it's underneath the square root. So we can rewrite it as 10 square root 4x squared times 3. It's the same thing. So we're going to pull out a 2x and leave the 3. So basically, when you're doing these kind of problems, you're almost doing what, like 3 multiplication problems in one? Something like that. All right, so that one's done. Any questions on it? You can always ask questions. All right, What I will tell you to watch out for, make sure you only multiply outsides and insides together. Never mix them. And number two, make sure once you get your answer, you check to see if it's in simplified form or not. Okay? Those are the two things you have to be careful of. All right, so this one is a little bit different. We're going to distribute it. And I actually think I'll start writing it at the top so we have enough room. So 3 times 4 gives us 12. And 5x times x will give us 5x squared. Minus 3 times 1 is 3. Square root 5x times 5 is 25x. But we're not done because now we can go through and pull things out. So we're going to have a 12x square root of 5 minus 3 times 5 square root of x. So when we clean it up, we get 12x square root of 5 minus 15 square root of x. So I'm really confused though. My indexes are the same. Why can't I simplify it anymore? Why do I have to stop there? Why is that my final answer? It's okay if my writing is a little bit sloppy and you can't really see it. What's the difference between the square root of 5 and the square root of x? My square roots match, right? They both have square roots in them. So why can't I go ahead and subtract? Why isn't my answer -3 something?
They have to stay the same.
Right, the radicands have to be the same. And right now they're not. You only have the square root part matching. The 5 and the x, those are different. So they did that on purpose to you, right? Okay. All right, so there they are a little bit nicer. They did theirs a little bit differently, I think. All right. So here's another version of the power property for radicals. If we have this, the nth root of x raised to the n power, what do you notice happens?
It cancels out.
It cancels out. So that's why whenever we're solving problems and you have a square root in your problem, if you isolate it to one side and then you square both sides, that's why they cancel. And that's really why we like doing that as mathematicians. You go, okay, we can do this. All right, so if we have to simplify this, which that's not really what I wanted to do right now. I wanted to solve, but that's okay. We'll get to it. Yeah, I don't like the order of this. Okay, so we're going to FOIL. X times x will give us x squared. Negative x root 3. Negative x root 3. Positive square root 3 squared. So x squared minus 2x square root of 3 plus 3. All right. That is the traditional foiling method that you are used to at this point, correct? That's basically what you're used to doing, except it's a little bit more picky because, of course, we're dealing with radicals. You will see in the next slide, much like I did when I was reviewing this yesterday to go over with you, that that is not the first approach they take. It definitely threw me for a loop, I can tell you that. So obviously I was going along like, hey, this is really great. I'm getting all these right, no problems. And then I get to this guy. And I was like, what did they just do? Okay, so this is where I said that we have this shortcut method. I don't teach it when I teach foiling, probably because I forget about it, but also because I think it's better to just teach foiling the traditional way. I will tell you that dealing with the radicals, the shortcut is kind of nice, especially when you don't want to like deal with everything. So I can say I have definitely used it. As you can see, we get the same answer, whether you foil it or you do it another way. Okay. All right, here is your warning. When we simplify the x plus k quantity squared, it is important to remember that the middle term, 2kx, be there. So don't just square the x and don't just square the k. I don't think I have to tell you guys that because you've been doing foiling for a minute, but there it is just in case. All right, to multiply two radicals that have different indexes but the same radicand, write the radicals in exponential form. Use exponential properties to simplify the expression involving exponents. Write the simplified expression in radical form. Here's your side note. We skipped chapter 5 because we cover it in 160. Last year when I was teaching this in person, much like this semester, I was going too fast. So I ended up teaching chapter 5. Chapter 5 basically is a repeat of exponents, except you do exponents and logs. So your counterparts last year had a little bit of an advantage to you on this one. But if you just practice exponents, you'll be good. And if you need any help, just obviously talk to me. Okay. So first things first, let's go through and distribute it, and then we'll figure out what we have to do. So 2 square root of x times the cubed root of x minus 2 square root of x times 5. That 5 is on the outside. So actually, let's just write it a bit better. 2 times 5, and we'll throw the square root of x on the end. Okay, so obviously we can simplify the second half of it. It's just negative 10 square root of x. But this is the section for why they say rewrite it in exponential form. So we have 2x to the 1/2 times x to the 1/3. Well, x and x are the same base, right? Which means we can bring those together. So to bring those two fractions together, we're going to add them. So that means we have to have the same denominator. Well, with 2 and 3, what's your GCF? I guess LCD. 2 and 3 will give you what?
6.
There you go. So 3 over 6 plus 2 over 6 minus 10 square root of x. Okay, so it's going to be 2 to the x to the 5/6 power minus 10 square root of x. Now, you can choose to leave it in exponential form. I'm going to take it back to radical form. If you do leave it in exponential form, like if it were on a test, make sure they're both in exponential form or both in radical form. Don't leave them mixed together. Just doesn't look nice. So I guess I won't really take any points off of you. Alrighty. What do you think we have to do for number 2? And this, by the way, is why I like their shortcut, because it's kind of shorter, because it's a shortcut, but it doesn't take as much room either. So we're going to use their shortcut. So we're going to do 3 cubed root of x squared plus 2 times, where's my paper? 2 times both terms. So 2 times the cubed root of x times 3 fifth root of x squared plus the last term squared. I hope you guys can see that. All right, so the cubed root of x squared, the squared term is the square is actually going to come in to be with the x. So it's going to be 3x squared. And you can write that in fractional form if you need to prove that to yourself, but that's how it works out.
Wait, where did you get the 2 from that's in front of the 2/3 x?
Oh, but no.
Okay, so you have to do that first.
No, yeah, this is using that shortcut.
Okay.
So you have to have this factor of 2 in here to use their shortcut method. If you don't like it, it sounds so funny. If you don't like it, tough. No, if you don't like it, you can use the traditional foiling method, but you're just going to end up having the same answer. You're just going to write it longer, if that makes sense. Okay. And because it's such a long problem anyway, I'm trying to fit it in. So I'm using the using their method. Okay. So to do this part, we do have to write the exponents as fractions. So we're going to have x to the 1/3, and then we'll have plus to the 2/5. And if you can't see where that came from, make sure you ask me, because I can definitely explain it. Just trying to save us a little bit of room. And then for the last part, we're going to get 9, it's 3 squared. And then we have to take and bring the 2 in with the squared term. So it'll be the 5th root of x to the 4th. Again, if you want to prove these two to yourself by practicing with your exponent rules, you may certainly do so. I'm just trying to simplify our process. So 1/3 plus 2/5. 3 and 5 will give us 15. So essentially, we're going to end up with 11/15. which means our index is going to be 15. And I can scroll down and show you guys the not so messy version of this. But that's basically the way it works. You guys want the cleaner version? Those of you that are writing, it's up to you. I think they just take more steps. And I believe this is going to be the last problems that we do for today. So if you want to take a look at the longer solution, a little bit neater, it's right here. And I believe you guys can take a look at that if you need to, especially if you're on the video. But yep, so we are going to actually, this is it, perfect timing. We will pick up on 9.3 Monday. So if you're paying attention to your homework, then you're able to do homeworks 9.1 and 9.2. And we'll start with 9.3 lesson on Monday. Before